Usually when we talk about something highly technical, whether it's, I don't know, a medical diagnosis or fixing a car engine or even writing software, there's this baked-in expectation of precision.
Right, yeah. Like there's a clear right and wrong answer.
Exactly. It's like engineering a bridge, you know? You calculate the load, you pour the concrete, and you know exactly how it's going to hold up.
Hmm.
Or like if you break your arm, the x-ray shows that jagged white line, and the doctor points to the screen and says, well, there it is. That's the problem.
It's binary. It's either broken or it's not. We find a lot of comfort in things being visible and solvable through a standard operating procedure.
Yeah, exactly. It's clean. But then you step into the world we are diving into today, and suddenly that x-ray machine is just entirely broken.
Oh, completely.
The bridge is literally shifting while you drive on it.
Yeah.
We are looking at a landscape that is incredibly murky, chaotic, and frankly, it's moving faster than anything we've seen in modern engineering.
It really is.
Like, I want you to imagine trying to build a remote-controlled airplane, but the entire sky, the actual invisible airwaves around the plane, is actively trying to hack it, blind it, and crash it all at the same time.
Right.
And the rules of how to stop that change, like every Tuesday, how do you even survive that environment?
Well, you evolve. I mean, you either adapt in a matter of hours or your multi-million-dollar program literally just falls out of the sky and becomes scrap metal.
So welcome to today's deep dive. We have an incredibly dense, massive stack of sources to go through with you today.
Tons of data.
Yeah, we are pulling from highly technical defense white papers, engineering system, architecture diagrams, raw frontline field reports.
The real heavy stuff.
Right. And our mission for this deep dive, we are going to unpack a hidden invisible war that is happening right over our heads. We are looking at the rapid, almost Darwinian evolution of drone technology and electronic warfare. And right now, the most intense crucible for this technology is the ongoing Russo-Ukrainian conflict.
And we should probably set some groundwork here, for the listener.
Oh, absolutely.
Because this isn't a conversation about drones as simple, remote control cameras anymore. What these white papers detail is a complete paradigm shift in how technology iterates under extreme existential pressure.
Right.
Modern combat is entirely rewriting the rule book for navigation, for secure data links, and maybe most surprisingly, for how agile software development actually works in the physical world.
And before we get deep into the engineering weeds, let's lay down a quick boundary for our discussion today.
Yeah, good idea.
Our source material obviously references the Russo-Ukrainian war heavily because, well, that's where the data is coming from right now. But our goal today is to treat these reports as a real-world engineering lab.
Exactly.
We are strictly analyzing the technological leaps, the physics problems, the tactical evolutions, just doing it objectively. We aren't endorsing any political viewpoints, we aren't taking sides, and we're not evaluating the geopolitical conflict itself.
Right, we're just here to convey the raw data and the ideas contained in these original source materials.
Exactly, just trying to understand the staggering pace of this tech.
Which is honestly the most valuable way to approach these documents. If you strip away the politics and just look purely through the lens of physics, thermodynamics, rapid innovation, you start to see trends that are going to impact global technology for, the next century.
Well, without a doubt. So to understand how these new hyper-advanced drones survive, we first have to understand what exactly is killing them in such massive numbers.
Right, you can't talk about the cure without understanding the disease.
Exactly. And that takes us straight into the intense electromagnetic environment of the modern battlefield. The sources refer to this as the invisible wall. We are talking about electronic warfare, or EW.
And, when people hear electronic warfare, they usually picture something out of a 1990s spy movie.
Oh yeah, like some guy in a van typing furiously on a keyboard to scramble a radio signal.
Right, exactly. But what's fascinating in these field reports is the sheer overwhelming scale and density of this EW ecosystem. It operates in massively overlapping layers that just blanket entire regions.
The scale is what really broke my brain a bit. Let's start at the top layer, like the strategic level. The sources highlight these massive Russian systems like the Krasuka-4.
Yeah, the Krasuka-4 is a perfect example of strategic level denial. This isn't targeting a single drone, it's targeting the airspace itself.
Wow.
It is designed to jam airborne radar, like AWACS planes, and low-orbit satellite communications from over 200 kilometers away.
Yeah.
It blasts the spectrum with so much noise that advanced radar systems simply go blind.
But then, okay, there's the Murmansk-BN system mentioned in that same section.
Yeah.
And the white papers claim this thing suppresses high-frequency communications over a 5,000-kilometer range.
Yeah, the numbers are wild.
I read that number and thought, okay, that has to be a typo. 5,000 kilometers, that's a continent-spanning footprint. How does a ground-based system even reach that far? Like the Earth curves?
It leverages the ionosphere.
Right, really?
Yeah, high frequency, or HF radio waves, they can bounce off the upper atmosphere to achieve these over-the-horizon ranges. The Murmansk BN is designed to pump out enough energy to disrupt those specific HF bands, which are often used for long-range military communications, naval coordination, global broadcasts across just vast distances.
Insane.
It's strategic noise. It's meant to degrade the command and control capabilities of entire theaters of operation, not just a single battlefield.
Okay, so you have this continent-level noise bouncing off the atmosphere, but then the reports zoom into the tactical level, down in the actual trenches, and it is just as chaotic, just highly localized.
Oh, absolutely.
You have systems like the Lear 3. This one really caught my attention because it doesn't just jam, it hijacks. The drone flies over a battlefield carrying an electronic payload that essentially acts as a fake cell phone tower.
Right, it's basically an airborne IMSI catcher.
Okay, explain that a bit.
So a cell phone is programmed to always connect to the tower with the strongest signal. The Lear 3 drone flies overhead, broadcasts a massive, overpowering 3G or 4G signal, and suddenly every smartphone in a targeted area connects to the drone instead of the local telecom network.
And once it has that connection, it can intercept communications or pinpoint the geographic location of those phones for artillery strikes, right?
Yes. Or even send targeted psychological warfare text messages directly to the soldiers' phones. It's weaponizing the very infrastructure we rely on every single day.
That is so creepy.
And that's just mid-level tactical.
Yeah.
If we push even further down to the individual vehicle level, the reports detail these fascinating microsystems with names like Volnores and Lesacek.
Yeah, I saw those pictures that look almost like little metal mushrooms magnetically mounted directly onto the hulls of tanks or armored personnel carriers.
Exactly. And their job is purely defensive, right? They aren't trying to hijack cell networks. They are just trying to keep the tank from getting blown up by an FPV drone.
So how do they work?
They essentially create a localized, omnidirectional bubble of electromagnetic noise. Imagine a force field of static with a radius of maybe 200 to 300 meters around the tank.
Okay.
Its entire purpose is to sever the control and video feeds of incoming first-person view, or FPV, drones. When the drone hits that bubble, the operator's screen instantly turns to snow, and the drone just loses its steering inputs.
But I think we need to carefully distinguish between the different types of invisible attacks happening within this wall, because the sources are really specific about this. There is a fundamental difference between jamming a drone and spoofing a drone.
Oh, definitely. It's the difference between brute force and deception. Jamming is exactly what those tank-mounted Volnores bubbles are doing. It's acoustic brute force in the radio spectrum.
Like just shouting really loud.
Yeah, it is screaming static at a specific frequency so loudly that the drone's receiver simply cannot hear the quiet, delicate whisper of a GPS satellite floating, 12,000 miles in orbit.
So if I'm the drone, it's like someone just put a pillow over my face and started screaming in my ear. I can't hear the instructions I need to fly.
Precisely. And when that happens, the drone's software usually has a failsafe. It realizes it's lost the navigation signal, so it either triggers an automatic forced landing, tries to hover in place until the battery dies, or relies on its internal compass to just try and fly a straight line back home.
But spoofing is entirely different. The white papers highlight the Russian Lima system for this. Spoofing isn't screaming static. It's much more insidious. It's lying.
That's a really great way to put it. Instead of blocking the signal, a spoofing system feeds the drone's navigation computer fake data.
Right.
It broadcasts counterfeit satellite ephemeris data, which is the data satellites use to tell receivers where they are in space, and it alters the timestamps.
So the drone isn't blind. The drone actually thinks everything is perfectly fine. It sees a full-strength signal. It thinks it has a perfect lock on 7 or 8 different satellites. But all of that data is entirely fabricated by a digital precision jammer sitting in a field somewhere.
Yes. The drone's internal algorithms take this fake data and mathematically calculate its position. It thinks, I'm I am at coordinates X and Y, flying at 500 feet. But the spoofing system is subtly shifting those coordinates.
Oh, wow.
It tricks the aircraft into veering miles off course. You can slowly walk a drone directly into an air defense trap or suddenly alter its altitude reading so it thinks it's 1,000 feet higher than it actually is, causing it to just dive straight into a hillside.
That's terrifying. And this leads to one of the most bizarre and dangerous geopolitical consequences that these white papers bring up. This invisible war does not respect physical borders.
No, it doesn't.
You can't exactly put up a chain-link fence for radio waves. The sources detail specific incidents in the Baltic region where this GNSS spoofing, global navigation satellite system spoofing, has inadvertently caused drones to completely lose their minds and veer wildly off course into unintended territory.
Right, we are seeing reports of stray drones ending up in NATO airspace, specifically places like Latvia, crashing near or directly threatening local infrastructure, like oil storage facilities.
And the drones didn't have those targets programmed.
No, they were lured there by a fake, distorted map of the sky.
See, I was trying to wrap my head around how spoofing actually pushes a drone into another country. It's not like the spoofer is using a joystick to fly the drone is flying itself.
Right, think of it like this. The drone's autopilot is programmed to fly a straight line north. The spoofing system slowly starts feeding it data that says, you are drifting east. You are drifting east. The drone's autopilot, trying to do its job, says, oh, I need to correct for that. So it steers further and further west to compensate for this fake eastward drift.
No.
It is actively flying itself into foreign airspace because it believes it is correcting an error.
It's an invisible spillover effect. The EW doesn't stop at the border crossing, and this presents a massive headache for international law, doesn't
A
it?
huge one.
From a legal perspective of state responsibility, even if a military isn't intentionally steering a drone into neighboring airspace, their active electronic warfare is the but-for cause of the drone getting lost.
Exactly.
Without the spoofing, the drone stays on course in the conflict zone. It completely blurs the lines of sovereignty and accidental escalation in ways our current legal frameworks seem totally unequipped to handle.
It creates a massive gray zone. If a spoofed drone crashes into a power plant in a neutral country, who is actually responsible? The side that launched the drone or the side that mathematically lied to its navigation system?
That's a tough question.
The engineering reports highlight this, not to solve the legal issue, of course, but to underscore just how chaotic the electromagnetic environment has become.
Okay, let's step back from the geopolitics for a second because I want to get to the core physical problem here. I was reading this section on signal suppression, and I found myself asking a really basic question.
Okay, what is it?
If the enemy is jamming my drone's video feed and control link, why can't I just build a stronger radio? Like, why can't I just turn up the power on my remote control, buy a massive battery, and punch my signal through their jamming noise?
Ecological question. I mean, in almost any other domain of war, you just bring a bigger hammer.
Right. If they have thicker armor, you build a bigger missile. Why doesn't that work for radio frequencies? And the answer the papers give is just pure, unforgiving physics. Specifically, the inverse square law of electromagnetic radiation.
Which is the fundamental physical barrier to outshouting a jammer. The received power of a radio signal drops exponentially the further you get from the transmitter.
Let me try an analogy here to see if I have the mechanics of this right.
Go for it.
Let's say you and I are standing in a massive, empty football stadium. You are standing all the way on the opposite side of the field, way up in the bleachers. I'm standing on the 50-yard line. You are the drone pilot, and I am the drone.
Okay, tracking so far.
You're trying to shout instructions to me. Even if you have a megaphone, a powerful transmitter, by the time your voice crosses that massive distance, the sound waves have spread out so much that they are just a faint whisper by the time they reach my ears.
Yeah, that is the distance degradation. The energy spreads out over a larger and larger spherical area as it travels.
Right. Now, introduce the jammer. The jammer is a guy standing exactly 1 foot away from my face, holding a compressed air horn. He doesn't need a massive power source. Because he is so incredibly close to the receiver, my ears, the energy from his air horn doesn't have time to dissipate. When he presses the button, the volume is deafening.
Exactly. Because the EW jammer, or the air horn, is sitting only a few hundred meters from the drone, and the drone pilot, the person with the megaphone, is sitting 10 kilometers away, the jammer has an insurmountable physical advantage.
Wow.
The jammer needs a fraction of a watt of power to completely dominate the receiver.
So brute forcing a stronger signal from miles away is physically impossible. To make your megaphone louder than the air horn directly in my ear, you wouldn't just need a bigger battery, you would need a transmitter the size of a nuclear power plant.
Yeah, you literally cannot carry enough power on a mobile platform to overcome the inverse square law when the jammer is in proximity to the receiver. And this quirk of physics creates one of the most terrifying cost asymmetries on the modern battlefield.
The economics of this are staggering.
Because it's so physically difficult to maintain control of a drone through that jamming, the ones that do slip through, or the ones that manage to operate in the gaps between the jamming bubbles, are incredibly lethal.
Right.
The sources highlight this with a brutal financial comparison. We are seeing $500 FPV drones built with off-the-shelf commercial motors and strapped with an RPG warhead, successfully destroying Russian Mi-20NM or Ki-52 attack helicopters.
I looked up the cost of those helicopters while reading the sources. Those are top-of-the-line aircraft. They cost between $18 and $25 million each.
Think about that math for a second. A piece of plastic that costs less than an iPhone can take out an aviation platform that costs as much as a medium-sized skyscraper. A 50 million to 1 return on investment.
And the threat is so severe, so existential, that the reports detail how the Russian military was forced to hastily adapt. They literally had mechanics out on the tarmac ripping apart these pristine, multi-million-dollar aerodynamic helicopters with welding torches to integrate heavy EW defense systems directly into the hulls.
Yeah, they initially tried just hanging EW pods on the outside on the weapon pylons. But these systems are bulky, they require a massive power draw, and they generate enormous aerodynamic drag.
Makes sense.
The helicopters were losing top speed and sacrificing critical flight range just to carry their own protective bubbles.
So they had to start cutting into the skin of the aircraft.
Exactly. They were forced to integrate the jammer arrays directly into the aerodynamic fairings just to survive a threat that didn't even exist a few years ago. It shows how desperation drives engineering.
Okay, so if the physics of the inverse square law dictate that we absolutely cannot outshout the EW jammers, how are the engineers on the drone side solving the problem? If the airwaves are entirely flooded with static and spoofed coordinates, what do you do?
Well, you teach the drone to go dark, you remove its reliance on the outside world, you teach it to fly completely blind and deaf.
This is where we enter the realm of GPS-denied environments, and honestly, this section of the white papers is where it starts to feel like science fiction.
It really does.
When the GNSS signal is denied, the drone can no longer ask satellites where it is. It has to switch to entirely passive internal systems. The primary method detailed in these architecture reports is something called VIO, Visual Inertial Odometry.
Let's break down how VIO actually works, because it's a masterclass in sensor fusion. It's essentially two separate systems compensating for each other's weaknesses. First, you have the inertial part. The drone uses high-frequency MEMS IMUs.
Microelectromechanical systems, inertial measurement units.
Right. These are tiny, highly sensitive, microscopic silicon structures, accelerometers, and gyroscopes built right into the circuit board. They measure every tiny physical shift in movement, hundreds of times a second.
Okay.
So if a gust of wind pushes the drone a fraction of an inch to the left, the IMU feels that acceleration.
So if it knows exactly where it started on the map when it took off and it perfectly measures every single millimeter it moves, it should know exactly where it is at all times.
We get a perfect vacuum, yes. But in reality, IMUs drift. They suffer from microscopic errors in measurement, and those errors compound. Imagine you are driving a car on a massive flat salt flat. You look at your compass, point the car exactly north, close your eyes, and hit the gas. You try to keep the steering wheel perfectly straight. For the first 10 seconds, you are probably still going north. But if your hand twitches even a millimeter, you introduce a tiny error.
Right.
After 5 minutes of driving blind, that tiny error has compounded, and you might be heading northeast. After an hour, you could be driving in circles.
That makes perfect sense. The longer the IMU goes without an outside reference to correct it, the more its math drifts from reality. Small errors accumulate over time.
So to fix the drift of the inertial sensors, you pair it with the visual part, cameras looking at the ground.
And this is where the math takes over. The reports mention these algorithms, EKF2 or EKF3, extended Kalman filters.
Yeah, the Kalman filter is one of the most important algorithms in modern engineering. It was used in the Apollo moon missions. It is fundamentally a mathematical judge that decides who to trust when you have noisy, imperfect data.
How does it do that in a drone, though?
The algorithm takes the data from the IMU, which is fast but drifts over time, and the data from the visual camera, which takes pictures of the ground rolling beneath it. The camera tracks features, like a distinctive rock or corner of a building, as they pass from the top of the video frame to the bottom.
Oh, I see.
The system knows the camera's frame rate and lens angle, so it calculates how fast the ground is moving.
So you have the motion sensor saying we are moving 50 miles per hour, and the camera saying, based on the pixels passing by, we are moving 48 miles per hour.
Yes. And the extended Kalman filter constantly cross-references them. It mathematically fuses these inputs to dynamically calculate the drone's absolute position, updating its best guess hundreds of times a second.
Wow.
According to the engineering specs of the sources, this tight coupling between the camera and the IMU can keep the drone's navigation drift to under 1.5% of its total flight path, entirely without GPS. If it flies 10 kilometers blind, it might only be off by 150 meters.
Which is incredible. But reading through the challenges section of the VIO implementation, I found a massive problem with relying on the camera. The sources call it the viewpoint distortion problem.
Yeah, it's a severe limitation of traditional image matching.
I was trying to picture this. The reports say these drones are flying extremely low, maybe 20 meters off the ground to stay under enemy radar coverage.
Right, very low.
But if they are using satellite maps preloaded into their memory to figure out where they are, the angles are completely wrong. A satellite map is taken from space, looking straight down at the roof of a house. But a drone flying 20 meters off the ground isn't looking at the roof.
Exactly, it's looking forward.
Yeah, at a 45-degree angle, it sees the side of the house, the windows, the shadows from the trees.
The geometry looks entirely different. Traditional 2D image matching fails completely at low altitudes. If the drone compares its angled video feed of a tree trunk to a satellite image of a green circle from above, the software won't recognize it as the same object.
So how do the engineers fix viewpoint distortion? If they can't match a picture, how does the drone know where it is?
They stopped looking at 2D pictures entirely. The engineers solved this by moving into the third dimension. They use particle filters and digital elevation models, or DEM.
Okay, what does that mean in practice?
Instead of matching pixels on a flat map, the drone uses its cameras, often stereoscopic cameras, to build a 3D structural height map of the terrain below it in real time.
So it's turning the video into a topographical map.
Exactly. It looks at the geometric shapes, the slopes of hills, the depth of valleys, the sheer vertical structures of buildings. It extracts the structural shape of the world and mathematically matches that 3D topography against a preloaded digital elevation model.
It's like it's reading the terrain like Braille.
Yeah, this is a good analogy.
It doesn't care what color the house is or what the shadows look like. It just feels the bump of the house, the dip of the road, and the rise of the hill, and checks that against the 3D map in its memory.
It is a brilliant way to bypass visual distortion. And it requires immense computational power to process that geometry in real time on a small drone.
And that Braille reading gets the drone to the general target area. It can navigate 10 kilometers blind and arrive over the right grid square. But what about the final dive? The terminal guidance phase?
That's the tricky part.
Right, you can't just blindly drop a munition over a general area if you are trying to hit a specific air defense radar or an artillery piece. If the operator's video feed is totally jammed, how does the drone actually find the target?
This is where Edge AI takes over. The reports specify the widespread use of highly efficient silicon, like NVIDIA Jetson chips, specifically the Orin series, mounted right onto the drone's circuit board. In the final moments of the flight, the drone completely cuts communication with the operator. It willingly goes into a man-out-of-the-loop autonomous mode.
It just takes the wheel.
It has to. The Edge AI runs highly optimized neural networks, like YOLO. You only look, one specifically iterations like YOLO 11, to process the live video feed from the nose camera in real time. The AI is looking for specific geometric features of high-value targets.
I was actually reading up on how YOLO works for this. It doesn't, see a tank the way a human does. It scans the pixels for contrast and edges. It looks for a vertical line meeting a horizontal line.
Exactly.
It builds a mathematical bounding box. It says, okay, this rectangle of pixels has the geometric proportions of a self-propelled artillery unit.
And once it establishes that bounding box and confirms a geometric confidence level, it locks on and steers the flight controls to dive into that box.
But the defense to this AI targeting is one of my favorite details in the entire stack of white papers, because it sounds so archaic. The sources detail a bizarre tactic being used on the front lines right now, painting military vehicles with high-contrast black and white zebra stripes.
It sounds absurd, but it is deeply rooted in how computer vision works.
It's literally dazzle camouflage from World War I. They used to paint battleships in crazy geometric shapes, so enemy submarines couldn't tell which direction the ship was moving. But now they're using it on tanks. Why?
Because the AI is looking for specific geometric edges. The goal of the zebra striping is to break up the visual geometry of the vehicle. As you said, the YOLO algorithm looks for a specific rectangular shape, or the clear edge where the turret meets the chassis.
But if you paint harsh, contrasting black and white lines diagonally across the vehicle,
You create hundreds of false edges. The camera sees sharp contrasts everywhere. The edge detection algorithms get overwhelmed with conflicting data. The mathematical bounding box falls apart.
wow.
The AI's geometric recognition fails. It can't achieve a high enough confidence score to classify the object as a tank, and it either misses completely or locks onto a decoy that doesn't have the paint job.
It's literally a bucket of paint defeating a sophisticated neural network. But of course, the engineers aren't just giving up and going home because of some zebra stripes. The iteration loop is too fast. The reports detail how they immediately developed decamouflage algorithms.
And this raises an important point about sensor fusion in AI. The response to visual camouflage was to stop relying solely on visual geometry. The decamouflage neural nets are trained on dual-mode inputs. They look at the visual camera, yes, but they simultaneously cross-reference that bounding box with a thermal imaging sensor.
Because you can paint the metal, but you can't paint the heat.
Exactly. Even if the zebra stripes perfectly distort the visual shape of the tank and confuse the edge detection, the AI looks at the thermal layer. It looks for the massive thermal signature of the diesel engine block heating up the rear deck.
Oh, that makes sense.
It looks for the hot exhaust gases. The algorithm verifies the target through its thermal footprint, completely bypassing the visual camouflage layer, reestablishes the lock, and autonomously initiates the final dive.
It's an incredible high-speed game of cat and mouse between paint and algorithms.
Right.
But relying purely on cameras, 3D height maps, and thermal AI is computationally heavy, it requires expensive sensors, and it's still fundamentally flying blind. Is there any way to actually fight back in the radio frequency spectrum? Like, is there a way to punch a hole in that invisible wall and get the GPS signal back?
There is, and it's heavily detailed in the engineering architectures. It's called a CRPA, a controlled reception pattern antenna.
Let's really unpack how this works, because I read the section on null steering and it felt like black magic to me. How does an antenna ignore a jammer?
To understand a CRPA, you first have to understand why a standard antenna fails. A standard basic antenna is fundamentally dumb. It's a piece of metal that just receives radio waves from every direction equally. If a jammer nearby is loud, the antenna just absorbs all that noise. It has no way to filter it out physically.
It's like an open microphone in a crowded room. It hears everything.
Precisely. A CRPA, however, is a smart array. It's not one antenna. It's usually made up of 4 to 16 individual smaller antenna elements arranged in a specific geometric pattern on a flat plate.
And it uses something called null steering.
Yes. The CRPA array is connected to a very powerful digital signal processor. When it detects a massive spike in power from an enemy jammer, it doesn't just get overwhelmed and shut down. The processor mathematically analyzes the incoming noise.
How?
Because the antenna elements are spaced a few inches apart, the jamming wave hits one element a tiny fraction of a microsecond before it hits the next one.
Oh, it uses the timing difference.
It analyzes the phase and amplitude of the jamming signal across the array to pinpoint exactly which direction the noise is coming from. Then it uses a technique called adaptive beamforming. The processor electronically alters how the antenna elements combine their signals. It introduces artificial phase delays to intentionally create destructive interference.
Destructive interference, meaning it creates a wave that is the exact opposite of the jamming wave to cancel it out, like noise-canceling headphones.
Very similar concept, but spatial.
Yeah.
It essentially creates an electronic null, a three-dimensional deaf spot or blind spot in its own reception pattern, pointing exactly at the bearing of the enemy jammer.
That is so cool.
The antenna physically still exists, but electronically, it simply refuses to listen in that specific direction. The jamming wave is canceled out before it ever reaches the GPS receiver.
That is brilliant. It just turns a deaf ear to the guy with the air horn.
And it gets better. Simultaneously, while it creates a dead zone facing the jammer, it focuses a high-gain beam, like cupping your hand behind your ear to hear better, directly upwards toward the real GNSS satellites.
So it does both at the same time?
Yes. The sources show these modern systems, like the E08 mentioned in the specs, can simultaneously track and suppress 3 to 7 independent jammers, located in different directions and across multiple frequency bands, while maintaining a perfect, delicate satellite lock.
It's dynamically reshaping its own hearing, but there is a massive catch highlighted in the policy section of these white papers. We can't talk about this tech without talking about geopolitics and supply chains.
No, we can't.
These CRPA antennas are incredibly effective, but they are heavily restricted by ITAR, the International Traffic in Arms Regulations.
Which is the U.S. regulatory regime for defense articles. Western countries heavily regulate the export of advanced CRPA technology because, well, you obviously don't want adversaries getting their hands on top-tier anti-jamming arrays.
But the reports note that this creates a huge supply chain bottleneck for allied nations who desperately need this tech on the front lines right now because it's so wrapped up in red tape they can't get enough of them.
Right.
The papers even point out this dark irony. Sometimes adversaries can acquire non-regulated commercial-grade CRPA equivalents from Chinese electronics markets easier and faster than allied nations can get ITAR-cleared systems from the West.
It's a classic procurement bottleneck, which is forcing a major shift in the industry. The papers document the frantic development of what they call non-red or domestic supply chains.
Okay, so building them locally.
Yeah. Allied defense industries in Europe and Ukraine are scrambling to build domestic, non-ITAR restricted CRPA alternatives. They're leveraging their own local semiconductor hubs and telecommunications engineers to build these arrays from scratch, ensuring they have a sovereign supply of anti-jamming tech that can't be choked off by foreign export laws.
Okay, so let's take a breath and look at where we are.
Now,
we have drones flying blind using visual odometry and 3D height maps. We have highly sophisticated AI using thermal fusion to bypass WWI-style zebra camouflage. And we have mathematically complex smart antennas reshaping their own radio waves to block out jammers.
it's a lot.
That is the bleeding-edge, high-tech Silicon Valley approach to surviving the invisible war.
It's solving complex math with more complex math.
Exactly. But what I absolutely love about this deep dive and what I found most surprising in the sources is that amidst all this AI and phase cancellation technology, the reports reveal a completely different, almost hilariously retro approach to the EW problem.
Oh, I know what you're talking about.
If the airwaves are utterly toxic with noise and spoofed data, why try to fight in the airwaves at all? Let's talk about the physical wire.
You are talking about the fiber optic drone. Without a doubt, it is one of the most disruptive and asymmetrical tactical shifts we've seen documented in these sources.
I am obsessed with this concept. It is so brilliantly simple, yet it completely breaks the modern battlefield. Instead of broadcasting a radio signal to a controller, the drone physically carries a spool of fiber optic cable glass or polymer that is thinner than fishing line. As it flies toward the target, it just spools out the wire behind it. We are talking about drones trailing 10 to 20 kilometers of wire, and some of the experimental prototypes detailed in the reports are pushing 50 to 65 kilometers of continuous spool.
It sounds absurd until you realize the tactical advantage is absolute. By transmitting all of the control inputs and the high-definition video feed through light pulses inside a physical shielded cable, the drone achieves zero radio emissions.
Right.
It is entirely invisible to radio direction-finding equipment. The enemy can't triangulate the pilot's location because there is no radio wave to track. And more importantly, it has total 100% immunity to any form of electromagnetic jamming or GPS spoofing.
The tank could turn on its Volnora's static bubble. The Krasuka 4 could be blasting the entire region. You could literally detonate an EMP next to this drone, and the video feed wouldn't even flicker.
Precisely. The invisible wall simply doesn't exist for a fiber optic drone. Furthermore, because it's fiber optic, there is zero latency and massive bandwidth. The operator gets a flawless, uncompressed, real-time 4K video feed.
Which is huge for the pilot.
In standard radio drones, the video gets choppy or lags as you get closer to the ground due to signal degradation and terrain masking. The fiber drone gives the operator perfect clarity right down to the centimeter, which allows for incredibly precise maneuvering in the final seconds of a strike. You can fly it straight through the open hatch of a vehicle.
The tactical impact of this retro tech is undeniable. The reports point specifically to data from the August 2024 Kursk offensive. Russian forces deployed these fiber optic drones extensively to target Ukrainian supply lines deep in the rear.
Yeah, we saw that shift happen very quickly.
Because the Ukrainian EW defenses were utterly useless against a physical glass cable, Russian operators were able to systematically hunt moving logistics vehicles with devastating precision.
The data from that sector indicates this single technological shift caused a 25% higher vehicle loss rate for Ukrainian forces in that specific operational window.
Wow.
It ultimately contributed to a severe logistics breakdown because the standard countermeasure, the electronic jammer, was rendered entirely obsolete overnight.
It's a massive game changer. But as I was reading further into this, I was trying to figure out the physical mechanics of it. How does a small drone carry 50 kilometers of wire? Glass is heavy. Wouldn't the weight of the spool drag the drone out of the sky?
That's the engineering challenge. The fiber used isn't the thick, heavily shielded cable you bury underground for residential internet. It is highly specialized, incredibly thin, bend-insensitive fiber. Often it's a polymer blend rather than pure silica glass to save weight and increase flexibility.
Okay, so it's much lighter.
The wire is so thin it's barely visible to the naked eye. The spool itself is wound with extreme precision, usually mounted directly under the drone's center of gravity. As the drone flies forward, the wire unspools from the center outward, with almost zero friction.
So it's not pulling the wire along the ground, it's just laying it in the air behind it.
Exactly. But it does introduce massive aerodynamic drag, especially if crosswinds catch the miles of trailing wire. The drone's motors have to work significantly harder, which drains the battery faster and reduces the overall payload capacity.
It's a trade-off.
Yeah, you sacrifice speed and bomb weight for absolute electronic immunity.
But this one specific innovation is causing some bizarre side effects globally. The sources point out a crazy economic shock that I never would have connected. The specific type of cable used for these drones is called G.657.A2 bend-insensitive single-mode fiber.
Oh, this part is fascinating.
Before this conflict escalated, a 50-kilometer spool of this stuff cost about $300 on the commercial market. Now, the reports say it's spiking over $2,500 a spool.
It's a classic supply and demand curve,
Yeah.
but with a massive modern twist.
Right. Because it's not just military demand driving the price up. The drone war is directly competing with the global boom in artificial intelligence. The massive warehouse-sized data centers being built by Silicon Valley giants to train large language models require the exact same type of high-density, bend-insensitive fiber optic cables to connect their millions of server racks.
You have state defense contractors building disposable kamikaze drones, bidding directly against multi-trillion-dollar tech giants building AI data centers for the exact same spool of glass thread. The global supply chain simply cannot produce it fast enough to satisfy both the battlefield and the cloud.
And beyond the economics, the white papers include a section on the severe ecological toll of this specific weapon. Think about the physical reality of a fiber optic drone. Every single time one of these is launched, it leaves behind 10 to 20 kilometers of synthetic polymer fiber draped haphazardly across the landscape.
It doesn't dissolve. It doesn't burn up.
No. The conflict is leaving literal spider webs of tens of thousands of kilometers of this incredibly strong, practically invisible wire across forests, agricultural fields, and ruined towns. The CEOBS, the Conflict and Environment Observatory, is sounding a massive alarm on this in our sources. It's an absolute nightmare for the local ecosystem.
Wildlife, particularly birds and larger mammals, are getting entangled in these invisible tripwires, leading to suffocation or starvation. Farmers trying to return to their fields are finding this microscopic wire getting sucked into agricultural combines, seizing up the gears and ruining expensive farming equipment.
Because it's stronger than steel at that diameter. It just wraps around the axles until the motor burns out. The reports warn it's creating a decades-long plastic pollution crisis in the soil. It's a sobering reminder that every technological leap in war leaves physical scars on the earth long after the fighting stops.
It is a profound environmental cost.
Yeah.
But even in the immediate tactical sense, the fiber optic drone isn't a flawless superweapon. The engineers quickly discovered a bizarre physical flaw when they first started deploying these in the field.
Oh, this is one of my favorite engineering anecdotes from the stack. So the drone carries an explosive warhead, usually a shaped charge to penetrate armor, and it carries a tightly wound, dense spool of fiber. Early on, the engineers figured, let's save space and make the drone more aerodynamic. Let's just pack the explosive charge right inside the hollow center of the fiber spool.
Makes perfect geometric sense.
Right.
In theory, on a CAD drawing, it makes perfect sense.
What?
But in practice, materials behave very differently under the extreme stress of detonation.
The field reports showed the drones were hitting the targets perfectly. The video feed would cut to black, but the tanks weren't being destroyed. The explosions were strangely weak. The engineers finally realized that when the warhead detonated, that densely packed, tightly wound coil of polymer fiber surrounding the explosive actually acted like a physical shock absorber.
It dampened the kinetic energy. Explosives require a solid casing, like steel, to build pressure and fragment outward as shrapnel, but polymer flexes and melts. the tightly wound fiber absorbed the blast wave.
That's so wild.
It acted almost like a Kevlar vest or a crumple zone in a car, severely ruining the fragmentation and armor-penetrating effect of the weapon. The drone would hit the target, but the explosion was literally muffled by its own wire.
I love that detail. So the engineers had to go back to the drawing board and invent what they call fragmentation shielding. They had designed physical metal barriers to isolate the spool from the warhead, directing the explosive energy forward and outward instead of letting it be absorbed by the plastic coil behind it. It just goes to show how many weird, unpredictable variables pop up when you take theory into real-world combat.
But it leads to the obvious tactical question. If the electronic jammers can't stop these wire-guided drones and the explosion issue is fixed, how do you defend against them?
Right. If you can't jam the signal, you have to break the drone or break the wire physically. And the sources describe the rapid deployment of incredibly low-tech physical defenses. We are talking about going from AI thermal targeting back to the Middle Ages.
The most cost-effective and rapidly deployed solution documented is literally draping massive, heavy-duty protective nets over critical roadways and suspending them above armored vehicles.
Giant fishing nets for drones.
Exactly. You physically entangle the drone's rotors before the shaped charge can get close enough to the armor to trigger. And for active defense, since the electronic force fields don't work, militaries have formed mobile fire groups.
I read about these guys. It's visceral. These are teams riding in pickup trucks equipped with radar warning receivers and acoustic sensors, microphones, listening for the specific high-pitched whine of drone propellers.
And when they hear the distinct buzz of the drone or see it on short-range radar, they don't use a jammer. They use shotguns. They use heavy machine guns. They throw up a dense physical wall of lead, a flak screen, to try and shoot the drone out of the sky using buckshot, or hoping a stray bullet severs the delicate fiber optic cable trailing behind it.
So let's step back and look at the big picture of what we've covered. We've gone from mathematical null steering antennas that cancel out radio waves, to AI reading 3D terrain maps, to 65 kilometers of trailing glass fishing line, all the way down to guys with shotguns and fishing nets.
It's quite the spectrum.
The sheer spectrum of technology is dizzying. But the most important question for me is, how are they doing this so fast? How are they iterating hardware and software at this speed?
That brings us to the final and perhaps most globally significant evolution detailed in these reports. It's not a weapon system, it's a methodology. The defense industry has fundamentally changed its operating model. They have completely adopted the playbook of the Silicon Valley software industry.
The traditional military procurement cycle, the way countries used to buy weapons, is dead.
Completely dead. Historically, developing a new weapon system took a decade. You write requirements, you bid it out to giant contractors, you build prototypes over 5 years, you test them, and maybe 10 years later it hits the battlefield.
Yeah, it was slow.
The sources explicitly state that in this conflict, the shelf life of military technology has shrunk from years to mere weeks.
Weeks. I want to walk through the iteration loop the reports describe because it's staggering. Imagine the enemy deploys a brand new EW jammer on a Tuesday. It uses a frequency nobody has seen before. Drones start dropping out of the sky. By Wednesday, a specialized recovery team has braved the front line to drag a crashed enemy drone or the jammer itself back to a lab.
Right. And by Thursday, hardware engineers have stripped it down and reverse engineered the new jamming frequency and the silicon running it.
Okay.
By Friday, software engineers have written a patch to counter it. And by Monday, every drone on the front line has been updated to ignore that new frequency. A multi-million-dollar defense advantage neutralized in 6 days.
It's agile software development, sprints, scrums, rapid prototyping applied to lethal hardware. The reports highlight the creation of these defense accelerators, like Ukraine's Brave One platform.
Brave One is a fascinating case study in removing friction. It acts as a direct, unmediated pipeline between the end user, the 20-year-old soldier holding the remote control in a freezing, muddy trench, and the software engineer sitting in a warm lab in the capital. There is no bureaucracy. There are no procurement boards.
The frontline operator opens an app and reports a problem. They say, hey, this specific motor burns out when I do evasive maneuvers, or this new jammer is dropping my video feed exactly at this altitude. The engineers get that data instantly.
And it's not just software that moves fast. The hardware iteration cycle has been revolutionized by advanced manufacturing. If the engineers realize they need a new aerodynamic shape for the drone body or a custom motor mount to handle a heavier battery, they don't have to wait 6 months for a heavy industry factory to retool its assembly line.
They use 3D printing. The reports specifically mention SLS, selective laser sintering. This isn't the cheap plastic 3D printer you have in your garage. This is industrial-grade lasers fusing nylon powder into incredibly strong, lightweight, aerospace-grade parts. They design the CAD file on Monday, print 500 copies of the new chassis by Wednesday, and have them on the battlefield by the weekend.
The hardware cycle takes 2 to 8 weeks, start to finish. The battlefield itself has become a giant, real-time industrial R&D lab with a brutally unforgiving feedback loop. If your design fails, people die. If it works, it becomes the new standard tomorrow.
But the software delivery is even faster than the hardware. They're fighting an OTA war over the air updates.
This is the most crucial concept in the entire stack of papers.
Think about it like this. It's like going to sleep and waking up to find your smartphone updated its operating system overnight to give you a cool new camera feature. Except in this case, a drone sitting in a damp bunker updates its firmware via a secure Wi-Fi hotspot, like a Starlink terminal, to survive a brand new missile defense system that was deployed yesterday.
It is an invisible, real-time arms race of algorithms. But pushing software updates to lethal weapons is incredibly dangerous. If you push a buggy update to a phone, the phone crashes. If you push a buggy update to a drone with a warhead, it might drop out of the sky on friendly troops.
So how do they test it so fast without killing their own people?
The reports detail the heavy use of digital twins and hardware in the loop, or HITL, testing. Before that over-the-air update is pushed to the trenches, engineers run the new code through massive, high-fidelity simulated environments. Software platforms like Gazebo 3D.
It's like a highly realistic video game engine.
Exactly. They take the new frequency hopping code and run it on a virtual drone in Gazebo. They test it against virtual crosswinds, simulated electronic jamming, and simulated motor failures. They run thousands of flight scenarios overnight. They use CI/CD pipelines, continuous integration, and continuous deployment. This is the exact same automated testing architecture that tech giants like Amazon or Netflix use to update their web servers without crashing the internet. But here, they are using it to push combat logic to thousands of lethal drones with a single click.
And all of this rapid iteration, this frictionless data sharing, is leading to the ultimate goal described in the final white paper: compressing the E08. Observe, orient, decide, act.
The fundamental cycle of all combat.
Historically, that loop took hours or days. A scout plane observes a target, flies back, develops the film, commanders orient themselves on a map, decide to strike, and act by calling in artillery. But now, the sources describe a real-time machine-to-machine network.
It's entirely automated. An Orlan 10 surveillance drone loitering at high altitude spots a target. The Edge AI onboard analyzes the pixels instantly, confirms the thermal signature of the vehicle, and calculates the precise GPS coordinates. It doesn't radio a human commander.
Wait, it doesn't?
No. It hands those coordinates off directly via encrypted data link to a Lancet 3 strike drone loitering 20 kilometers away.
The strike drone receives the data, calculates the intercept vector, and initiates the dive in a matter of seconds. It completely bypasses human latency. The machines are observing, deciding, and acting. The humans are just supervising the network.
And that leads to a profound, almost chilling realization about what we are truly reading in these white papers. We aren't just looking at the evolution of disposable military hardware in a localized conflict.
We are looking at a ruthless Darwinian proving ground for the future of all autonomous technology.
Yes.
Let's recap this massive journey because we've covered incredible ground today. We started with the unyielding physical limits of radio waves, why you mathematically cannot outshout an EW jammer because of the inverse square law, and how that creates a terrifying cost asymmetry where a $500 drone kills a $20 million helicopter. We saw how brilliant engineers solve that physics problem by teaching drones to fly completely blind, using visual inertial odometry to read the terrain like Braille, and thermal AI to bypass WWI-style zebra camouflage.
We explored the incredible, disruptive retro solution of the fiber optic drone, trailing 50 kilometers of physical glass fiber to achieve absolute, unbreakable electromagnetic immunity and the strange economic and ecological ripples that is causing globally.
And finally, we saw how the Silicon Valley model of agile development, 3D printing, and over-the-air software updates is keeping these systems alive, compressing a 10-year procurement cycle into a 6-day iteration loop.
Which leaves us with a final, vital question to ponder based on everything we've read. If military hardware is now iterating at the speed of a Silicon Valley app update, what happens when this agile warfare methodology and this deeply battle-tested technology bleeds back into the civilian world?
Oh, wow. That is a heavy thought.
Think about it. The massive tech companies building our future delivery drones our autonomous Waymo cars navigating city streets, our commercial AI systems, the core technologies powering them, navigating without GPS, using AI to identify objects through visual clutter, coordinating autonomously in machine-to-machine swarms. Those technologies are currently being stress-tested and perfected in the most hostile, unforgiving electronic environment on Earth.
They are learning to survive in a sky that is actively trying to kill them.
Exactly. And when this hardened, hyper-optimized, battle-tested technology comes home and fully integrates into the civilian sector, our civilian airspace, our logistics networks, and our daily interaction with autonomous machines will fundamentally transform. The technology isn't just surviving the hostile sky, it's mastering it.
And eventually, that sky is coming to us. It really makes you look at that little remote control airplane or the delivery drone dropping off a package in a completely different light.
It definitely does.
Well, thank you so much for joining us on this massive deep dive. We hope we helped make this murky landscape a little clearer for you. As always, keep questioning, keep learning, and stay curious. We'll catch you next time.